Hi folks, let's try the Leetcode 273 today, integer to English words, and it has been classified as hard. It's kind of, I would say, it has been asked in some of the interviews. In fact, it was asked to me just last week by one of these, the heroes of software engineering. So I would say that it's a very interesting problem as well. It's a very practical problem because when you write checks, you have to write these numbers in English words. So it's kind of pretty interesting there as well. So we should definitely try to get this under our belt. And so, how do we do it? So, how do we do that is let's first try to read the problem before we even try to solve it. So it's a convert a non-negative integer to its English words representation. Given input is guaranteed to be less than 2 raised to the power 31 minus 1. That tells us that we will not be given numbers that cannot be the positive numbers or starting from 0 and the positive numbers that can not be represented in a signed 32-bit integer. So that's pretty good news for us because that means we do not have to worry about anything more than a billion, in the order of billions. So that's fine. Now let's look at the example. And the example is saying is input is 123 and the output is 123. Makes sense? 1 2 3 4 5 is 12,345. Makes sense. Now let's go to 1 2 3 4 5 6 7, and similarly this can be represented as 1,234,567, right? And then 1 2 3, and this one is 1,234,000,000 blah blah blah, right? So it is all looking good. The things are clear to us. So let's try to solve this problem. So one thing we have to understand is that this problem can be solved if we start by representing certain numbers. Like for example, from 0 to 19, we have to have a dictionary for this. Dictionary to represent for the English words for these, right? Because these are kind of primitives. Basically the idea is you start with as few numbers whose English representation you would have to have and then build from there. So basically start with some basic primitives and then build on top of that. So now we come to, so that is that. But suppose if you're given a number like 23, how can we represent that? And that can be represented as 20. So for example, 20, now if we go to our dictionary that we just tried to define, that would not take care of that because there is no 20 in that. So that means we would need numbers for 20, 30, etc., right? So, and then if for example 23, if we had these numbers 20, 30, and then we have to go to this one to get the representation for 3. So that means we would need at least a dictionary, and then we may need another dictionary, or we might need a list, because if you had a dictionary for this 20s and 30s, how are you going to index it? You have to do some more manipulations. Like imagine you get 2 in the integer division, 23 slash 10, 2 and 3. So 3 we will get from there, and 2 how do we get? We can't index into this because that will give us 2 and 2, not 20. So for that we would have to probably use this as a list. So let's do that, and we will start by defining a dictionary, and then we would have a list. So let's so ideally this would be more like this. We will say, we'll call our dictionary as D1. We will say 0 is 0, and then we will have 1 as 1, and so on and so forth until you hit I would say 19. And so I do not want to bore you guys, so let's take it from this my notes here. So we would go straight and just have this right here, and that should take care of this issue right here. So let's okay, so there we have our dictionary representing numbers from 0 to 19. Now let's have a list for things like 20, 30s and 40s. So for that we would need something like this. Sorry, 20, 30 and so on and so forth, right? So that's gonna be another list, and I do not want to bore you guys, so let's take it from here. And so there we go. So that's our list. So we have our, now let's start to see how we start. So then I'm assuming we can start by looking at this number that is passed to us. And if so let's say if we are given numbers in the range 0 to 19, our job is very easy. All we need to do is say if num less than 20, we are in business. All we need to say is return d1 num, right? And else if, so for numbers less than 20, we are in good shape. We have, it's pretty much trivial. You just simply have to index the dictionary and give you the right number. Now for the numbers over 20 and up to like 99, we have to have a special case, and which is going to be, if so we say if num is less than 100, that means up to numbers 99, all we need to do is we can say return. So the idea is to index into the list, because okay, so before we even do that, how are we going to index this? So if you have heard of a function known as dibmod, now what dibmod does is it gives you the remainder and the integer division, the whole part of the division in one shot, rather than having to do a mod first to get the remainder and then do integer division for the complete part of the uh, division. So let's not use these two separate operators. We can simply use a dibmod. So so we just say result equal to dibmod, and then we say num 10. So and then all we need to do is we can say we can index our dictionary with res 0. So now here you see, for a number like 23, we would get 2 and 3, right? 2 would be the res 0 and 3 will be res 1. So L1 res 0, but you see if you say 2, then it will go to 0, 1, 2, 40, but we want 20. So that's kind of a little bit of hack here, I would say. You just in the list you have to index by doing a -2 on your not the remainder but the divisor part. So here we are. So no, not the divisor would be the number that 10 here in this case, but basically the whole integer part of the division. So this plus, now here there is a trick, and the trick is if we were to just do something like d1 res 0, suppose if I just did this, then what happens is that that oh sorry, not first of all, it is not res, it has to be res 1, because we are like for 23, so this is the place where we pass 3 here to get 3, actual 3 for the integer 3. So what is the problem with this thing? The problem with this thing is it will work fine for like a case like 23. But if you had like 20, what would happen? You'll get 2 and 0. And 0, that means instead of writing 20 as just 20, it would write 20 and then 0. Suppose if we just do something like plus, just in case we want to have a space in between. And so this will write 20 0. This is not what we want. So basically we need a way to conditionally put this space. And how do we do that? That can be done by Python being such a awesome language. Lets us do something like this, that this we say we can say that we can put this expression plus this if not res1. So if res1 here, our remainder was 0, then we need not put anything and we are done. We don't even have to do a secondary lookup or anything like that. So else, all we need to do is we can say space. We need to put actually a space, and then we will need to do a lookup. So, and then we can say d1 res1. How is that? So you will see that with this we should be able to take care of numbers that are up to and then let us assume that for this at this point we just simply, before we build the whole function, we can simply say else. Let us just say we say print number too big, suppose we say, or number out of range. And that is pretty cool here. As you all know how to do a printf kind of thing in Python, we just have to do a format and then we have to say num. Right, now you see, let's try to run some simple test cases, see what are we saying here so far. So it is failing obviously because we can only handle numbers less than 100. So let us change our test case to see if it will pass for something like 23. There you go. So it did accept 23. And now let's give another, just for the heck of it. Let's put 99. All right. So it has accepted 99 as well. Let's change the test case. Give 0. Okay, that works. Now let's do something like 80. And that works as well. So that is, so far it's looking good. Now let's go to the let's try to handle numbers greater than 100 or 100 and greater than 100. So that's else num less than. Now what we would do is, after we have taken care of numbers which are greater than up to 100, we go straight to 1000, up to 1000. And because 1000 we have to represent by the word like 100 and 1000 and things like that. So up to 9999, we know 999, we know that all we need is a new addition to our so-called numbers alphabet or numbers dictionary or numbers list of string constants for different numbers. And for that we can simply put the like for example, after, so we have this so far, but to have a number like 123 we need the word 100. So we have to add that now, and now is the time where we take care of the case like. So anyway, now we do div mod 100 this time, because we are so, what would happen is, for something like, just to give you an example, for something like 823 or 844, we will get something like 8 and 54. So let's see how we can basically represent that. So we can say return, we have to, for 8, something like 8 or something like any of this first part of the result or div mod, because it's rest 0 and rest 1, we can simply do a dictionary lookup. We can say d1 rest 0 plus, and for the part that is like 54, or the remainder of this div mod in this case, we can again use the same trick. And the trick is what we just did in the case of numbers less than 100, but there we were able to get away with just a dictionary lookup. But now we have something like 54, and we know how to represent numbers up to 54 because we just did up to line 12. So we can probably do a recursive call, and so basically it would be exactly this thing, but instead of just doing a lookup, you would be doing a recursive call here. And the recursive call will be self dot numbers to words. Call this function again and pass it uh, just ras1. How is that? And that should take care for the numbers up to 1000, but not 1000 itself, because we do not have the, oh, so return this plus, oh, I see, we have issue here. We should have said we have to have this string 100 here, right? Because it's like so 100, we do need this for the numbers up to 1000, we would need the 100 also. So let's do this. We will have to add this 100. Okay, so this should take care of numbers up to 999. If you want to see that, let's do the run code. And he said else. Okay, so we have issue here. We have to have elif, not else. Okay. All right, let's give it a number which is now we know we can handle, something like 123, and see if it prints the right result. Okay, so that is taken care. Let's take something like 120. Okay, so that is taken care as well. How about 999? Okay, so that is fine, and it's all looking good. Maybe we can try 900. Okay, so that is looking good as well. So let's try to now go for the numbers higher than 999, basically 1000 and more, because now we will have to introduce a new word in our lexicon, and that is 1000. And basically from now on the function is very simple. All we need to do is we can simply say here, okay, one more thing, we went from 100 to 1000, but as you know, in English there are no separate words for, like, specific words for 100,000, like in some languages, like in India, in Hindi, I think they have lakh is for lakh, lakh is for 100,000, but this is no, this is just English, and they do not have the word for lakh. They go straight from after 100, they go to million, and the million means we add 3 more zeros to our 1000, and that takes care of. And then we will do a ras equal to, in this time we will do a div mod with 1000, and that will give us again here, this will give us res 0, for example, in this case would be the actual result of the division, and the res 1 would be the remainder. So res 1 is remainder and res 0 is the division result, right? So now again, we simply, in this case, what we will have to do is, now you see, when we have a number which is, like for example, 1234. Now when you divide that by 1000, you will get 1 and 234, right? And 234 we know how to handle up to line number 15 by these three cases. So all we need to do is, we need to have a similar call, and but instead of just a simple lookup here, we may have to do, I think we will have to do a, here we can say 1000. By the way, it's 1000, not thousands. So I had this confusion that should we say, for example, 1000 but 5000s. No, but apparently in English you do not say thousands, you say thousand. There are some situations where you can say thousand, but not for numbers. Like you do not say 36,000, you say 36,000. And so that is good for us. All we need to do is change the code here to say that we would have to do a recursive call here, which is that we will have to do something like this. Except that we need to have a 0 here. So return self dot number towards res 0 plus 1000, and again we have this trick here. Please do not be confused by this. All it is there is for, because we do not want to do a recursive lookup if our remainder is 0, because that will unnecessarily force us to do a call for something which we do not want, because 0 will get 0, but we do not want to put a 0 unless the only time the word 0 should be used is when the number passed is 0 itself, but not when the remainder is 0 and things like that, because that will unnecessarily introduce a 0 in the sentence, and this is not good. So now with this we should be able to take care of cases for up to more than 1000, and we want to, let's try one of these now. Let's try something like 1 2 3 4. Alright, so that is taken care of, and if I change it to 1230, does it put a 0 in there, or just say, okay, so that is looking good now. So we can handle numbers up to in fact, let's try this case here, because this is a number that is less than million. So let's run code and give this number and see what happens. So we have 12,345. So this is where we are in good shape. Everything is looking good up to million now. So we are in business for the numbers up to million. We have to now see how we can take care of a billion. And for billion, all we need to have is basically increase 3 more zeros into the cases that we have so far. So we just take this. You see, I wonder, it was kind of, they classified it as hard, but I would say once you get the hang of the problem, it's not hard at all. It seems like, you see, I'm just cutting and pasting code. Once you have a few basic cases taken care here up to numbers, I would say 100, then it's just a question of a recursive lookup. So with this, we are now ready to take care of numbers, except we should not forget that we have to have a million here. I think that was a problem right here, because instead of saying thousand, we actually wrote we have to have for up to billion, we have to have here, I think. So that was 100, that is 1000. Now we need to have million here, right? So that takes care of things here. Now we have to go for the billions, and what is the that will take, I think this should take care of number like this one. We will see what happens. So let's try to do it. And okay, let's change our test case, see if it handles the numbers that are larger. Okay, so that's the wrong answer he's saying, because why? Because we did not change our, see what is going on here, 100, 1000 and million. So okay, and then the bug has been introduced because we did a division here by 1000. We should have, okay, now I should take care of this test case. There you go. So all looking good. So now let's go to the progressively higher numbers. So we have taken care of numbers less than a billion. So now let's go for the numbers that are more than a billion, and for that we simply cut and paste here. And what is going on here? I think we just have to take this from here onward, and once we come here we say LL. Okay, so we just add 3 more zeros, and here we also add 3 more zeros, and here we just change it to billion. You see how magically everything is working once you build the basic test cases. And so that should take care of this number, and we would throw it in. But first let's see, we haven't broken anything. So that's looking good. Now let's change the okay, let's change the test case to see if we can handle a number that is more than a billion. There you go, there you go. So looks like we have taken care of all the cases for numbers up to I would say in the order of billions, and our function is looking good. So we should try to now submit this code and see if it works, and we are good to go. So let's see that. All right, that's and the greatest news that we have heard on this Sunday, and our lead coding has been a success, thundering success, I would say. I hope you guys had fun doing this problem, and continue lead coding, continue solving harder and harder algorithms and the problems related to them. I would say keep learning about the newer algorithms and keep solving the problems which are progressively harder. And hopefully we'll bring more of these hard, so-called hard lead code problems in the future. But until then, I wish you guys a great success in your interview journey, and I'll see you next time. Bye bye.